In the previous lecture, we discussed quantum point contact based charge sensors and charge sensing mechanism in quantum dots. In this lecture, we will discuss single electron transistor based charge sensors and various kinds of single electron transistors, normal, superconducting and semiconducting single electron transistors. In the previous lecture, we discussed quantum point contact based charge sensors and charge sensing techniques in quantum dots. In this lecture, we will discuss single electron transistor based charge sensors. We also will look into the details of normal, semiconducting and superconducting single electron transistors. Single electron transistors are basically quantum dots. Usually, when we say single electron transistor, those are always large quantum dots where you observe Coulomb blockade. And the term quantum dots are generally reserved for systems where you see single particle levels. And quite often, single electron transistors refer to charge sensing quantum dots. And quantum dots refers to the system where you are studying the dynamics of the charges. The term SETs or single electron transistors usually refers to the charge sensor. It could be metallic, semiconducting or superconducting. And usually those are larger quantum dots compared to the quantum dots that you use for quantum circuit applications such as spin qubits. Here is a simple circuit model for the quantum dot system. I would say a single electron transistor where you have a quantum dot which is connected to the source and drain through tunnel junctions and also coupled to a gate through a capacitor. These source and drain tunnel junctions have capacitance CS and CD and resistance RS and RD respectively. And one important feature of these quantum dots are the Coulomb blockade oscillations. These are the Coulomb blockade oscillations which exhibit very sharp change in its current, in the current through the device for a small change of gate voltage. This is exactly the feature that one would utilize for charge sensing, where the current through the single electron transistor sharply varies for a very small change in the gate voltage, or I would say very small change in the electric field or the potential felt by the potential change felt by the single electron transistor. Here is a SEM micrograph, scanning electron microscope picture of an aluminum oxide aluminum tunnel junction system or single electron transistor, which is basically turned in normal state by the application of a magnetic field. Okay, so this system shown here is a single electron transistor that we are referring to, where we have two tunnel junctions here. There is one here and there is one here, and which is connected to the source and drain region, and you have this small island in the middle, that is the quantum dot. And in this diagram you can see a bunch of other tunnel junctions too, which are not our focus for this discussion. you can see another single electron transistor here, with two tunnel junctions and an island. Okay, and a gate here for that. There is a gate here which is coupled to this island. It's shown here. Okay, and the current voltage characteristics which we learn will observe a blockade which you can lift by applying a gate voltage. These different traces shown here are for different gate voltages. So you have a complete blockade transport in the center region, which you can lift by changing the gate voltage, and you can get a nearly ohmic behavior. This is the IV characteristics, the current voltage characteristics, whereas these are the Coulomb blockade oscillations, where gate voltage versus the conductance is plotted in this diagram. And this device has a resistance of 195 kilo ohm in the normal state. That means these two tunnel junctions together is giving you a resistance of 195 kilo ohm, which is more than the resistance quantum for the combined system. So you need to have R, S and D greater than the resistance quantum or quantized resistance, that is 25.813 kilo ohm for observing Coulomb blockade oscillations and seeing the charging effects. So these junctions are more or less symmetric, and you can assume that each of these has close to 100 kilo ohm resistance, these two junctions, which is more than the resistance quantum required for observing the Coulomb blockade oscillation. So you have 195 kilo ohm. So you can if the junctions are symmetric, you can say 95 to 100 kilo ohm for both junctions, with each of them now is more than the resistance quantum, which is required for observing Coulomb blockade oscillations and charging effect. Okay, this is the situation for a normal state single electron transistor, and the point here is the sharp change in the conductance through the device as a function of very small change in the electric field or the potential in the vicinity of the device is utilized for detecting the charge motion. Okay. Now let's discuss the case of a superconducting single electron transistor. For a normal metal or semiconductor single electron transistor, the IV trace is going to look something like this, where you have a blockade region which you can lift by the application of a gate voltage, and this width of this blockade region is going to give you the charging energy. Here is a general circuit representation of a single electron transistor, where the island is connected to source and drain, as we just discussed in the previous slide, through tunnel junctions. And we also learned in one of the previous modules that there is a tunnel resistance requirement to observe Coulomb blockade. That is, this resistance should be more than 25.813 kilo ohm, which is the quantized resistance value. But now, for a superconducting system, the charge carriers are Cooper pairs, and the tunnel resistance is h by 2e all squared or h by 4e squared, which is around 6.45 kilo ohm, not 25.813 kilo ohm. It is 1/4 of 25.813 kilo ohm. What that means is, to observe Coulomb blockade or charging effect of transport which involves Cooper pair, you require only 6.45 kilo ohm. You don't require the 25.813 kilo ohm as the junction resistances. But to observe charging effects of quasi-particles or electrons in the system, which generally is available once you are above the superconducting gap, you still require the 25.813 kilo ohm as the resistance of the tunnel junctions. Okay. But the IV trace of a superconducting tunnel junction system involves superconducting gap also. So generalized picture here is you have a middle blockade region which is because of the superconducting gap. Then there is a rise in the current, and this region you can observe the Coulomb blockade because this is where you have quasi-particles available or electrons available. So in this region you will observe charging effects of quasi-particles or charging effects of electrons. Okay, but in this region, flat region in the middle, you have other kinds of transport mechanism which involves Cooper pairs also. In this region, in the middle, where Cooper pairs are available, you can observe charging effects of Cooper pairs for a system with lower resistance, 6.45 kilo. But with this resistance for the tunnel junction, you will not observe the charging effects of quasi-particles because for quasi-particles, you need to satisfy this condition, and for Cooper pairs, you need only this much resistance of tunnel junctions. For example, in this case, what you have is you have a tunnel junction system which is taken from the superconducting state to normal state by the application of a magnetic field. So when you apply the field, the superconducting, the features associated with the Cooper pair transport, these are the Josephson quasi-particle cycle and double Josephson quasi-particle cycle, which are not going to be a part of our discussion, but these features involve sequential tunneling of Cooper pairs and quasi-particles, which are actually signatures of correlated transport involving both the electrons and Cooper pairs. Okay, here the IV traces are showing. I was showing the effect of both charging effects of both Cooper pairs and quasi-particle. Whereas above the gap, that is somewhere here, you can see this is because of the charging effect of electrons or quasi-particle. But the moment you apply magnetic field, you can see that the whole IV, this point has been shifted to here by the superconducting gap. So whatever the feature that you are seeing in this region, those are all because of the transport mechanism involving both Cooper pairs and quasi-particles. Okay, so the charging effects of Cooper pair transport features involving Cooper pairs are seen until the edge of the superconducting gap. Okay, and the moment you cross the gap, you have only electrons in the system, and then the quantum dot is going to exhibit charging effects of only electrons. So the point here is, in a nutshell, the charging effects of the quasi-particles is shifted above the superconducting gap the moment you have superconductivity. The moment you turn off the superconductivity, in this case by the application of a magnetic field, you can see the whole curve is shifted back to the origin. Okay, so you can bring a superconducting SET to normal state and observe the charging effects of only quasi-particle by the application of a magnetic field. But quite often, a superconducting SET is preferred over normal state SET because you need to have only lower resistance to see the charging effects of Cooper pairs, whereas the quasi-particle charging effects requires a higher resistance, which will have detrimental effects for various technologies. Okay, we just learned that the tunnel resistance requirement for observing charging effect of transport feature involving Cooper pair is not the 25.8 kilo ohm, but it is 1/4 of that because of the Cooper pair charge. It is around 6.45 kilo ohms. So in this experiment, it is very clearly demonstrated that by reducing the tunnel junction resistance from a state which is above 25.8 kilo ohm per junction to far below that, almost half of that, you can retain the transport features which involves quasi-particles, but the charging effects that you observe above the gap should be somewhere here in this case, above the gap is diminished gradually and it is absent when you have much lower resistance, that is around 24 kilo ohm total. Okay. So what we have here is a superconducting single electron transistor made of aluminum oxide, aluminum island, aluminum electrodes and aluminum oxide tunnel junction. Here is the island and you have tunnel junctions at these 2 points, okay, and you have source and drain and the gates are here. Now in this case you have total resistance of 58 kilo ohm and these tunnel junctions are more or less symmetric and identical, so you can assume this is close to maybe 29 kilo ohm per junction, maybe something like 29 kilo ohm per junction. Okay, so you can observe both charging effects of quasi-particle that is above the gap. So gap is in this range. Okay, and below the gap you have transport features where both Cooper pairs and quasi-particles are involved. This is called double junction quasi-particle cycle, and this is double Josephson quasi-particle cycle, and this is Josephson quasi-particle cycle. Okay, this is also called 3E cycle too. Okay, because you have Cooper pair and one Cooper pair, one electron going through both junctions. In effect, you are transferring 3 electrons through the system. That's called 3E cycle. Here you have Josephson quasi-particle cycle where you have one Josephson tunneling through one junction and quasi-particle tunneling also involved in other junction. Okay, that's what it is. So this is called Josephson quasi-particle cycle. This is double Josephson quasi-particle cycle. Okay. Anyway, those are details which we will not go dwell into much in this lecture. So now when you reduce the resistance to 38 kilo ohm, that is approximately, you can say 19 kilo ohm per junction. Okay, you are getting this feature stronger. You can see a strong subgap feature because now you have reduced the junction resistance. You have enhanced the Josephson tunneling effect. Okay, but you have almost lost the charging effects of quasi-particle because your resistance requirement is now very weak. It is not satisfied. You have only 19 kilo ohm per junction, whereas you are supposed to have 25 kilo ohm per junction to have strong charging effects of quasi-particles. And further, if you reduce the junction resistance, then you have lost completely the charging effects of quasi-particles, but you have made these even stronger. Okay, these subgap features, the DJQP and DJQP feature, you have made even stronger. Okay, so in nutshell, what you have is resistance greater than h by e square, you have charging effects of both quasi-particles and Cooper pairs. R less than h by e square, you have Coulomb blockade only for Cooper pair or Cooper features involving tunneling of Cooper pair, but no Coulomb blockade for quasi-particle. That is the situation in these two cases. Okay. Now, what we have done so far is we discussed the basics of single electron transistor, both in the normal and the superconducting state. Okay. Now let's review a couple of situations where these superconducting, semiconducting, and semi-metal single electron transistors are used for charge sensing in quantum dots. Let's first briefly look at the charge sensing of a graphene quantum dot using a graphene single electron transistor. Okay, what we have is a quantum dot defined out of etched graphene, and everything is graphene here. Okay, the whole device is defined by etching and shaping the graphene sheet. Okay, so you have a quantum dot here, which is relatively small, and you have SET here, which is much larger. As I discussed, single electron transistor generally is referred for larger quantum dots. For our smaller quantum dots are the system under study, which you always call quantum dot. And you have source and drain region for the quantum dot here, and source and drain region for the SET here. And this is a schematic or diagram of these two device configuration. So these two devices are capacitively coupled. Now here, this is the conductance through the dot, which is showing the Coulomb blockade oscillation as a function of the side gate SG, and this is the conductance of the single electron transistor taken simultaneously. So you can see wherever you have charging and discharging events, which are the Coulomb blockade peaks, you have exactly at the same point you have fluctuations or sudden changes in the conduction of the SET. Now, a small thing what you need to keep in mind here is you have an overall oscillation, a slow oscillation here, and you have a fast oscillation or changes in this case. The reason for the slow oscillation is, see, this gate, which is used to vary the potential of the dot, also affects the potential of this single electron transistor. Both of these are Coulomb blockade devices. So when you vary this gate, you not only observe Coulomb blockade oscillation for transport through the system, but you also will observe Coulomb blockade oscillation for transport through this system also. And this is going to be much slower because this gate is further and this dot is larger. Okay, in both cases, you're going to see this basically effect of this gate to this single electron transistor will be much weaker than this one because it's much farther compared to compared to where the dot is. Okay, so the slow oscillation that you are seeing is because the Coulomb blockade oscillation effects of the sensor, and the fast oscillation correspond to the charging and discharging events in the graphene quantum dot. Okay, and just to get rid of this, what you can do is you can take a differential conductance with respect to this gate of the SET. So this gate is basically changing the potential of the dot here and also the SET here. And if you directly take a local measurement of this Coulomb blockade effect, what you will see is you can get rid of this slow oscillation, and it's going to basically sense only the slope changes. And you can see all these sudden changes in the conductance of the SET coincides with the Coulomb blockade oscillation of the dot. And as I mentioned, there are many places where you don't see conductance oscillation, because those are not detectable or current levels are very low, you can see here, but this SET is going to capture almost all of those things. Here, what you have is a Coulomb diamond plot taken from the direct current or direct transport measurement from the graphene quantum dot. And this is basically the same plot where you have recorded the changes in the SET conductance. And you can see that whatever the feature that you see here, you can extract all those features with a higher level of clarity when you use a charge sensor. Okay, so this is an example where a semi-metal SET is used to detect charging and discharging events or charge sensing in a semi-metal quantum dot, in a graphene SET and a graphene quantum dot. Okay. Now, let us look at a semiconductor SET on a semiconductor quantum dot. In this case, what you have is an intrinsic silicon quantum dot and intrinsic silicon SET. So this quantum dot and SET both are defined on a nanowire geometry. So what you have is a thin silicon strip which is defined by micro fabrication process, and a similar SET also. Okay, so these quantum dots are defined by applying voltages on these gates. So you have two gates B, L and B, R. Those are the barrier gates which defines a quantum dot. You have a quantum dot here, you have an SET here. But in this case, both are very similar, and both have a similar geometry and similar size also. Okay, so when you vary the gate, you can observe the charging effects of in the quantum dot by measuring the SET conductance, and you can also create a Coulomb blockade diamond also using the sensor. Here, this is the conductance of the quantum dot, but this is the conductance of the quantum dot sensed by the SET. As I told before, though we have both these quantum dots and SETs are in this case very similar in size, usually sensors are referred to as SET and quantum dots are your system that you are studying. Okay, you are probing. Now, just to finish, let us take a look at charge sensing using a superconducting single electron transistor on a double quantum dot system. Okay, so in this case, what you have is you have two quantum dots. You have quantum dot 1 and quantum dot 2 defined by the gating technique. Okay, and if you look carefully, you will see a weak signal, weak image. These are aluminum tunnel junction system. Okay, and this is the gate for the SET, and there is an edge here which makes sure that these electrons in the quantum dot does not escape out here. So the path for electrons is dot 1, dot 2 and goes out, and the sensor extends onto one of the dot just to improve the capacitive coupling. Okay, the sensor island here is extended to, you can see a weak image, a feeble image of a line which is going on top of the quantum dot. That is to improve the capacitive coupling. Okay, so now let's look at a single electron charging events, and then we will also discuss the double dot, single electron charging events, and then we will look at double dot. Okay, charging events. So in this first set of measurement, you have only one quantum dot. So this set of gates are not energized. So you have only these 5 gates energized. Then these are the Coulomb blockade oscillation, which is the conductance through the dot as a function of the gate voltage. And as we mentioned in the previous lecture, can see the oscillation amplitude is going down because you are making the gates negative, so you are making the tunnel barriers thicker. So you start with a really thin tunnel barrier, and the tunnel barrier becomes really thick as you make the gates more negative. So the transport actually gets, transport gets weaker and low, and the current gets very low, and it is almost immeasurable in this range. But you can see that the Coulomb blockade oscillation of the SET taken simultaneously with this data is showing all these charging events which correspond to the charging events of the dot. All these will have one-to-one correspondence. And wherever, at the same place, wherever you don't have any Coulomb blockade oscillations or charging events absent, but this SET is still showing that you have plenty of tunneling events going through. That is because the tunnel barriers got really thick in this regime, and your current measurement is not able to capture the charging and discharging events of the quantum dot, but the sensor, which is capacitively coupled dot, captures all those oscillations, all those charging events very clearly. Okay, this is exactly why you need a charge sensor for this kind of measurements. And as I mentioned in the previous slide, this data also shows a slow oscillation, that is this oscillation, okay, that is because of the direct coupling of the dot gate to the IISER island here. And whereas these small blips or faster oscillations are because of the charging and discharging events on the dot, which is captured by the SET. Okay, and now you can turn on the other quantum dot by turning on this gate, these two gates. Then what you're going to have is a charge stability diagram, which is actually a honeycomb-like diagram. So if you take a sweep of both gates together, that you have gate VG1 plus VG2, if you see both together, that is these two gates, this one and this one here, okay, these plunger gates, this one, these two, and you see those two together, what you're going to do is, say you have a charge stability diagram which is looking like a honeycomb, right? It's going to look like this. Like this. So when you, and the next honeycomb is here, okay, and when you see both of these gates together, that is VG1 and VG2, this is the VG1 VG2 space, okay. Now when you see both of these together, what you're doing is you are going to this axis, because you're at a 45-degree in your charge stability diagram. If you remember what we have discussed in the double dot, during the double dot discussion. So when you do that, you are going in this direction through the stability diagram. So you have double peaks, okay. You have split peaks in the Coulomb blockade oscillation, because you are observing now the Coulomb blockade oscillation of both dots together. So this gate voltage here means you are varying both gates at the same time. So each of this peak is going to split into two. That's what you're seeing here. Okay, you can see that each of these are actually double peaks. Okay, each of these peak correspond to the nearby triple points in the charge stability diagram. And when you capture, this is the current through the double dot, and when you observe the current through the SET, as you can see, that you have this slow oscillation, that is because of the Coulomb blockade oscillation of the SET. But you can see that there are peaks here. All these blips earlier, those were like a single, single peaks. Now all those have now split into two. You can see all of these have some cusp shape. That is because it's capturing these cusp shape charging events directly. So the SET is sensing the each of the charging events, because the reason that you get triple point is you have two kinds of charge configuration in the stability diagram. Okay, so these two the SET can very clearly resolve. That is what this data is telling. Okay, so in nutshell, so far what we have discussed is the charge sensing using single electron transistor. Single electron transistors can come in normal, superconducting, semiconducting, semi-metal, whatever format, okay, whatever system, okay. But what you are doing here is you are using the strong nonlinearity of the Coulomb-Bloch oscillation to sense the charge fluctuation in the nearby device, okay. And I just want to mention here that these single electron transistors are a lot more sensitive compared to the quantum point contact transistors that we have discussed in the previous lecture. But at the same time, this single electron transistor comes with an extra expense, that is, these are separate systems, and these have a lot more gates and a lot more since it's very sensitive, and the sensitive because they are another Coulomb blockade device as opposed to the quantum point contact, which has a very large, linear regime where the single electron transistor is sensitive only on the Coulomb blockade, on the sides of the Coulomb blockade oscillation, which is a much narrower sensitive regime where the device is sensitive. Okay, that is one thing. Second thing is single electron transistors themselves are Coulomb blockade devices, so the charging and discharging events in that device can actually affect the system that you are trying to probe, because you are trying to probe the oscillation in the potential energy due to charging and discharging events, right? But the sensor itself has that oscillation, and so this can actually act back onto other system too. So there is an extra piece of interesting neat physics there, which we will try to touch upon in one of the coming lectures. All right, okay.